In the deep cosmos of Andromeda, a galaxy emerges like ripples in the cosmic sea, where the dance and light of stars converge. Andromeda cradles a sense of mystery. With a soft glow, countless stars illuminate the path of the galaxy. The brilliance of starlight surpasses the galaxy, captivating our eyes with its beauty. The embrace of Andromeda is vast and profound, filled with the mysteries of the universe. The enigmatic tales of Andromeda, beyond the reach of our eyes. What lies in the future of Andromeda? Revealing a different aspect of the cosmos? In the galaxy of Andromeda, where the spectacle of light and darkness continues. Today, in our 7th session of Introduction to Astronomy, we will explore the astonishing identity of the Andromeda Galaxy and contemplate the fate of galaxies. Subscriptions and likes greatly empower our video production. The Andromeda Galaxy is the closest giant spiral galaxy to our Milky Way, situated approximately 2.5 million light-years away from Earth. With a diameter of about 220,000 light-years, it is roughly twice the size of our Milky Way. Andromeda Galaxy boasts around 1 trillion stars, with some being much brighter and younger than those in our own Milky Way. At its center lies a supermassive black hole, surrounded by a bulging region filled with stars, dust, and gas, as well as a flat, rotating disk. The spiral arms extending from the disk showcase the galaxy's history of star formation. Andromeda Galaxy is accompanied by several satellite galaxies, among which the largest ones include M32, M110, and M33, exhibiting elliptical or spiral shapes. Formed through the merger of various primitive galaxies approximately 10 billion years ago, Andromeda Galaxy stands as one of the oldest galaxies formed after the Big Bang. In about 4.5 billion years, it is anticipated to collide with our Milky Way, giving rise to a new, massive galaxy. Information about the planets existing in the Andromeda Galaxy is still not well known. With approximately 1 trillion stars in the Andromeda Galaxy, it is presumed that some of them may have planetary systems. However, observing planets in the Andromeda Galaxy is extremely challenging. This difficulty arises from the fact that Andromeda is located about 2.5 million light-years away from Earth, making the planets appear very faint or even invisible. Research on giant planets within the Andromeda Galaxy is still in its early stages. In 2009, a candidate planet was discovered orbiting a star in the Andromeda Galaxy. This candidate planet, considered the first one found in the Andromeda Galaxy, is estimated to be a giant planet with about 6.4 times the mass of Jupiter. It appears to orbit a star known as M31 in 2008-12A in the Andromeda Galaxy, which is considered a new type of recurrent nova that explodes annually. As our understanding of the Andromeda Galaxy's planetary systems is limited, ongoing research and advancements in technology may provide more insights into the presence and characteristics of planets within this distant galaxy. In 2013, 2 additional candidate planets were discovered orbiting another star in the Andromeda Galaxy. These planetary candidates represent the second and third such findings in the Andromeda Galaxy, estimated to be Earth-sized planets with approximately 0.7 and 0.6 times the mass of Earth, respectively. These candidates appear to orbit the star M32001 in the Andromeda Galaxy, which is part of the satellite galaxy M32. It's important to note that these planetary candidates have not been definitively classified as planets. They were discovered using a method called microlensing, which utilizes the phenomenon of bending the light of a star when it aligns with a planet. While this method allows for the inference of a planet's presence, obtaining detailed information such as its size, mass, and orbit is challenging. Additionally, microlensing is a one-time event, making it nearly impossible to reobserve the candidate planets. To gather more information about planets in the Andromeda Galaxy, more powerful and precise observational instruments are needed. Space telescopes currently in development, such as the James Webb Space Telescope or the LUVOIR Space Telescope, could contribute to exploring the planets in the Andromeda Galaxy. I'll provide a detailed explanation of the collision between the Andromeda Galaxy and our Milky Way. The Andromeda Galaxy and the Milky Way are the two largest galaxies in the local group, gravitationally attracted to each other. Currently, the Andromeda Galaxy is approaching our Milky Way at a speed of approximately 120 km per second, and they are expected to collide in about 3.8 billion years. The collision between the Andromeda Galaxy and the Milky Way is anticipated to unfold through the following scenarios. Initial stages: as the two galaxies approach each other, their respective spiral arms begin to twist and stretch. The supermassive black holes at the centers of each galaxy start gravitationally attracting surrounding gas and stars, forming accretion disks. The accretion disks produce intense radiation, leading to the birth of new stars. First collision: when the two galaxies first collide, the stars in each galaxy scatter, and the gases mix, triggering a vigorous phase of star formation. During this phase, there is a 12% chance that our solar system might escape the gravitational influence of the Milky Way and a 3% chance of being incorporated into the gravitational field of the Andromeda Galaxy. However, due to the vast distances between stars, the likelihood of significant effects on our solar system is minimal. Intermediate stages: after the initial collision, the galaxies pass through each other, and their gravitational forces cause them to turn around for a second collision. The spiral arms of both galaxies transform into massive tidal tails and scatter into space. Additionally, the supermassive black holes at the centers of each galaxy approach each other, emitting strong gravitational waves. Second collision: when the galaxies collide for the second time, the stars mix, and the gases merge, initiating another phase of intense star formation. During this stage, there is a high likelihood that our solar system will be relocated to the outer halo of the new galaxy. The supermassive black holes at the centers also merge, emitting colossal gravitational waves. Final stage: upon complete merger, a new giant elliptical galaxy is born, known as Milkomeda. Milkomeda has a mass approximately 8 million times that of the Sun and is characterized by a low central density compared to existing elliptical galaxies. It possesses a massive halo composed of stars remaining from the spiral arms and tidal tails of the Milky Way and the Andromeda Galaxy. This collision and merger will result in the formation of a new, larger galaxy that incorporates elements from both the Milky Way and the Andromeda Galaxy. IC 1101 is the largest known galaxy in the universe, surpassing even the Andromeda Galaxy. It is about 50 times larger than our Milky Way, with over 100 trillion stars. Situated approximately 1 billion light-years away, IC 1101 is considered one of the oldest galaxies in the cosmos. IC 1101 has grown to its colossal size by absorbing other galaxies, mainly consisting of aging yellow or orange stars. At its core lies a supermassive black hole with a mass equivalent to 400 billion suns. Currently, IC 1101 is in a state of decline, no longer producing new stars. The process of a galaxy's demise entails the cessation of star formation, gradual extinction of existing stars, and the possible loss of raw materials like hydrogen gas due to interactions, mergers, or other disruptive events within the galaxy. It's crucial to distinguish the concept of a galaxy's demise from the Big Crunch. The Big Crunch is a hypothesis about the ultimate fate of the universe, suggesting that if the gravitational forces due to matter are stronger than the expansive energy, the universe might contract back to a single point. However, current observations indicate that the universe's density is much lower than the critical density, and its expansion is accelerating, making the likelihood of a Big Crunch very low in current cosmological theories. The death of a galaxy does not necessarily result in only black holes remaining. Instead, it signifies the cessation of new star formation, and existing stars gradually fade away through various processes. Smaller, cooler stars may become red dwarfs and persist for an extended period. Slightly larger stars might evolve into planetary nebulae or white dwarfs, cooling down over time. Stars significantly larger than the Sun could undergo supernova explosions, potentially forming black holes or neutron stars. Therefore, in the process of a galaxy's decline, the exclusive dominance of black holes is not guaranteed. Black holes represent just one outcome in the diverse life cycles of stars, and not all stars end their lives as black holes. Additionally, black holes themselves are not eternal. According to physicist Stephen Hawking's theory of Hawking radiation, they can gradually evaporate over billions of years.
In the azure glow of our galaxy, the mystical door is opening wide. In the cosmic factory, where the world unfolds, shining stars are being crafted. Stars, tiny seeds of miracles, blossoming in the folds of time, dancing in the radiant symphony of life. Yet, even in the darkness, stars that have lost their light are weeping. We must seek out those stars. I want to know why the stars have disappeared. Why have imperfect beings lost their light in the cosmic factory? Stars bear our dreams and hopes, but darkness is sweeping them away. In the factory of stars, efforts are made to create better stars for us. We must reclaim that light. We must seek out stars that should not exist. Those stars threaten our existence. Yet, there must be reasons behind their existence. Unveiling the mysteries of the cosmic universe. Embarking on a journey to reclaim the light. Beneath the canopy of a single starlight, we will all find each other. Subscribing and liking greatly empower the creation of content. Hello, today I will provide a detailed explanation about our galaxy. Our galaxy is a vast collection of stars known as the Milky Way, to which our solar system belongs. The galaxy is also referred to as the Milky Way. The origin of our galaxy dates back approximately 13.8 billion years to the time of the Big Bang. The Big Bang is considered the birth of the universe, during which the incredibly small universe rapidly expanded, leading to the formation of energy and matter. Some of this material eventually contributed to the formation of our galaxy. Our galaxy is characterized by its distinctive spiral shape, with a flat disk and spiral arms extending outward from a central bulge. These spiral arms, known as the spiral arms, radiate from the central hub. The Milky Way is home to around 100 billion stars and rotates around the center, known as the Hubble plus 20 center, driven by gravitational forces. The Milky Way consists of various components, with stars and dust being among the most prominent. The galaxy hosts stars of varying sizes and shapes, all held together by gravity. Dust consists of tiny particles generated in space, and a significant amount of dust exists within our galaxy. Additionally, the Milky Way contains gas and a central region known as the Hubble plus 20 center. This rotation is maintained by gravity. Our solar system is located in the Milky Way galaxy. In reality, our solar system is situated toward the outer edge of the Milky Way. Moving from this outer region toward the center of the galaxy, there are various celestial objects beyond our solar system. However, due to the vast distances involved, these objects have minimal impact on our solar system, which remains relatively stable in its orbit. As for the future of the Milky Way, accurate predictions are challenging, but astronomers anticipate that our galaxy will continue to expand as part of the evolving universe. Furthermore, approximately 4 billion years from now, a collision with the Andromeda galaxy is predicted. This collision will eventually lead to the merger of the two galaxies. I will provide an English translation for the information you provided about the Alpha Centauri system and the Large Magellanic Cloud. Alpha Centauri refers to the brightest and largest galaxy among the satellite galaxies of our Milky Way. The Alpha Centauri of our galaxy is known as the Large Magellanic Cloud, LMC, situated approximately 160,000 light-years away from Earth. The Large Magellanic Cloud is a much smaller spiral galaxy compared to our Milky Way, with a diameter of about 14,000 light-years and an estimated 100 billion stars. The gravitational influence of our Milky Way has caused the Large Magellanic Cloud to distort and stretch, forming many regions where new stars are born. Visible to the naked eye in the southern hemisphere, it is renowned as the brightest galaxy in the night sky. The Alpha Centauri system includes Proxima Centauri, which is part of our Milky Way. Proxima Centauri, a red dwarf star, is the brightest and largest galaxy among the satellites, forming the Alpha Centauri system alongside the Large Magellanic Cloud. Proxima Centauri is significantly smaller and fainter than the Sun and is the closest star to Earth after the Sun. Proxima Centauri is known for its variability in brightness due to its flare activity and emits strong X-rays. Within the habitable zone of Proxima Centauri, a potentially habitable exoplanet called Proxima b has been discovered. Please note that the information provided is based on the details you shared, and any updates or additional context may be necessary for a more comprehensive understanding. The term Betelgeuse giant planet refers to the possibility of the existence of a massive planet around Betelgeuse, a red supergiant star. Betelgeuse is the 8th brightest star in the night sky and corresponds to the shoulder of the Orion constellation. It is about 1,000 times larger than the Sun and located approximately 550 light-years away. Giant planets are typically composed of gases or ices rather than rocks, and examples from our solar system include Jupiter and Saturn. The presence of a giant planet around Betelgeuse has not been conclusively proven. However, some researchers suggest that the sudden decrease in Betelgeuse's brightness may be attributed to the passage of a giant planet. For instance, a research team analyzing data collected by Japan's meteorological satellite Himawari 8 from 2017 to 2021 discovered that the brightness decrease of Betelgeuse repeats with a 400-day cycle. They propose that this phenomenon could be explained by the shadow of a giant planet orbiting around Betelgeuse. Research on the Betelgeuse giant planet is still in its early stages, and more accurate observations and modeling are required. The study of Betelgeuse's characteristics and the planet formation process is expected to contribute to a better understanding of these phenomena. There are many fascinating planets in our Milky Way galaxy with diverse characteristics. For example, 55 Cancri b, one of the closest exoplanets to the solar system, located about 40 light-years away. This planet orbits a G-type main sequence star that is approximately 25% larger than the Sun. With a mass roughly 8 times that of Jupiter, 55 Cancri b is a giant gas planet composed of hydrogen and helium. Due to its surface temperature of about 2000 degrees Celsius, it is suggested that carbon on the planet might crystallize into diamonds, forming part of its structure. HD 189733b, referred to as a hot Jupiter, this planet is situated about 63 light-years away from Earth. It orbits a K-type main sequence star that is about 13% smaller than the Sun. With a mass approximately 1.1 times that of Jupiter, HD 189733b has a surface temperature of around 1000 degrees Celsius. It is known for having glass particles in its atmosphere, leading to the speculation of glass rain on the planet. PSR B1257+12b, this planet orbits a pulsar, PSR B1257+12, which is the remnant of a star that underwent a supernova explosion. Located about 2,300 light-years away, this planet has a mass approximately 0.02 times that of Earth. Being the first exoplanet discovered in our galaxy, it is exposed to the intense radiation from the pulsar and is also known as a pulsar planet. These planets showcase the incredible diversity and unique features found among the many celestial bodies in our Milky Way. I will provide an English translation for the information you provided about the factors that make certain star systems in our galaxy more likely to host extraterrestrial life. To search for extraterrestrial life, it is crucial to determine whether there are planets with environments conducive to life. Typically, conditions that would support life include appropriate temperature and pressure. Life forms find it challenging to thrive in extreme temperatures or pressure conditions that are too high or too low. Therefore, planets within a certain distance from a star, maintaining suitable temperatures and pressures, are considered within the habitable zone. This is also known as the Goldilocks zone. Liquid water. Life as we know it relies on water as a solvent for chemical reactions. Planets hosting life should have liquid water, as it is essential for various biological processes. This water can exist on the planet's surface or underground. Suitable chemical composition. Life forms are composed of specific elements, and these elements need to be available on the planet's surface or in its atmosphere. For example, life on Earth requires elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and others. These elements may be present through geological processes, atmospheric composition, or cosmic radiation. Studying star systems with these conditions increases the likelihood of finding extraterrestrial life, as they provide the necessary environmental factors for life as we understand it. Ongoing advancements in astronomical research and technology continue to enhance our understanding of exoplanets and their potential habitability. Star systems that meet the conditions for potentially hosting extraterrestrial life include Proxima Centauri, the closest star system to Earth, located approximately 4.2 light-years away. Proxima Centauri is a red dwarf star, much smaller and dimmer than the Sun. It has a known exoplanet called Proxima Centauri b, situated within the habitable zone. This planet is speculated to have liquid water and a potential atmosphere composed of carbon and nitrogen. TRAPPIST-1, a red dwarf star about 39 light-years away from Earth. This system is known to have 7 Earth-sized planets, 3 of which are within the habitable zone. The potential for liquid water and atmospheres rich in carbon and nitrogen is high on these planets. Gliese 667c, a red dwarf star located approximately 23 light-years away. Part of the trinary system Gliese 667, this star has 6 known planets, with 3 of them situated within the habitable zone. These planets are speculated to have liquid water and atmospheres composed of carbon and nitrogen. In addition to these, numerous star systems exist within our Milky Way, and some of them may harbor planets with conditions suitable for extraterrestrial life. Now, let me provide an explanation about black holes within our galaxy. Black holes are celestial objects with gravitational forces so intense that not even light can escape from them. They can form when stars undergo explosive events or mergers, and they come in various sizes and masses. In our Milky Way, there are several types of black holes, including stellar black holes, formed from the collapse of massive stars. Intermediate black holes, with masses between stellar and supermassive black holes. Supermassive black holes, found at the centers of galaxies, including our Milky Way's Sagittarius A. Black holes are intriguing astronomical phenomena, and their study contributes to our understanding of gravity, space-time, and the life cycle of stars in our galaxy. Sagittarius A, a supermassive black hole located at the center of our Milky Way galaxy. Sagittarius A has a mass approximately 4 million times that of the Sun. Situated around 26,000 light-years away from Earth, it attracts surrounding gas and dust, forming an accretion disk. This accretion disk emits bright light due to high temperature and pressure, allowing observers to detect the outline of the black hole through this emitted light. X-ray binaries. It is estimated that there are thousands of small black holes in our Milky Way, most of which are believed to form binary systems with other stars. Black holes in binary systems absorb material from nearby stars, emitting intense X-rays in the process. Observing these X-rays helps confirm the presence of a black hole. For instance, the X-ray binary system GRS 1915+105, located about 6,000 light-years away from the galactic center, consists of a black hole with roughly 14 times the mass of the Sun and a companion star with about 0.8 times the mass of the Sun. Gravitational wave binaries. In our galaxy, there are binary systems emitting gravitational waves during the process of black hole mergers. Gravitational waves are ripples in spacetime caused by the motion of extreme celestial objects like black holes or neutron stars. Through the detection of gravitational waves, we can learn about the existence and characteristics of black holes. For example, the gravitational wave signal GW 150914, observed in 2015, originated from the merger of 2 black holes with masses around 36 and 29 times that of the Sun, respectively. Supernova. A supernova is an explosive event that occurs when a massive star reaches the end of its life cycle. This explosion is triggered by the collapse of the star's core under the force of gravity, ejecting the outer layers into space. The energy and material released during a supernova can contribute to the formation of new stars and planets. In our galaxy, it is estimated that about 3 supernova explosions occur per century. Neutron star. Neutron stars are dense remnants left behind after a supernova explosion. Composed almost entirely of neutrons, these compact objects typically have a mass about twice that of the Sun but a size smaller than Earth. The density of a neutron star is comparable to that of atomic nuclei, and its surface gravity is approximately 10-11 times that of Earth. It is estimated that there are around 300 million neutron stars in our galaxy. Pulsar. Pulsars are a specific type of neutron star that rapidly rotates and emits intense beams of electromagnetic radiation. Pulsars can rotate hundreds to thousands of times per second, releasing particles at speeds close to the speed of light. These particles are channeled by the pulsar's magnetic field, creating beams of light. The rotation axis of a pulsar does not necessarily align with its magnetic axis, causing the beams to appear as if they are flashing when observed. It is estimated that there are around 200,000 pulsars in our galaxy. These celestial phenomena play crucial roles in the life cycle of stars, contributing to the enrichment of the interstellar medium and influencing the formation of new celestial bodies in our Milky Way. Star factories in our galaxy, pillars of creation and more. A star factory refers to a region where new stars are actively forming, predominantly found within interstellar clouds composed of gas and dust. These clouds undergo compression and heating due to the gravitational pull of stars, leading to the formation of protostars that eventually ignite nuclear fusion reactions. This process unfolds over millions to billions of years. In our Milky Way, numerous star factories exist, and here are some notable examples. Pillars of creation. The pillars of creation are part of the Eagle Nebula, captured in an iconic image by the Hubble Space Telescope. Composed of interstellar gas and dust, these pillars stretch approximately 4 light-years in length. They are in the process of creating new stars while being eroded by the light of nearby, recently formed stars. The pillars of creation are located about 7,000 light-years away from Earth and have been imaged in the infrared spectrum by the James Webb Space Telescope. Orion Nebula. The Orion Nebula is one of the most prominent nebulae visible in the night sky, situated in the Sword of Orion constellation. It is approximately 1,500 light-years away and has a diameter of around 24 light-years. This relatively young nebula, formed about 100,000 years ago, is actively giving birth to new stars. Observations of the Orion Nebula have been conducted using the Hubble Space Telescope and the James Webb Space Telescope across various wavelengths. Carina Nebula. The Carina Nebula, one of the largest and brightest nebulae in our galaxy, is located in the Carina constellation. It is situated around 7,500 light-years away and has a diameter of about 200 light-years. Formed approximately 3 million years ago, the Carina Nebula is a stellar nursery where around 14,000 new stars are currently being born. Imaging of the Carina Nebula has been performed using the Hubble Space Telescope and the James Webb Space Telescope at different wavelengths. These star-forming regions offer insights into the dynamic processes shaping our galaxy and contribute to the continuous evolution of cosmic structures. Challenges and contradictions in the Big Bang Theory. The Big Bang Theory posits that the universe originated from a point of explosion approximately 13.7 billion years ago. However, certain celestial bodies and observations seem to challenge or contradict aspects of this theory. For instance, in the Orion Nebula, over 150 objects were discovered drifting in space without a central star. These objects, estimated to be young and hot, with masses several times that of Jupiter, defy traditional theories of planet and star formation. Furthermore, some argue that while the cosmic microwave background radiation is considered strong evidence for the Big Bang, it can also pose challenges. The observed amount of lithium in the universe, derived from primordial nucleosynthesis predictions, does not align with theoretical expectations, creating a discrepancy. As anomalies emerge, the Big Bang Theory undergoes revisions, necessitating adjustments or supplementary theories. However, the absence of observational support for these proposed modifications poses a challenge. There are reports of unidentified ultra-high-energy cosmic rays, reaching energy levels deemed incompatible with current physics. These cosmic rays, if validated, highlight phenomena beyond the scope of contemporary understanding. In essence, celestial entities that defy expectations according to the Big Bang Theory serve as indicators of its limitations or inconsistencies. It's crucial to acknowledge that the Big Bang Theory is a hypothesis about the origin and evolution of the universe and is not necessarily an absolute truth. Considering alternative possibilities remains an open avenue for exploration. Unexplained celestial entities beyond scientific expectations. In the vast cosmos, there exist peculiar celestial entities that defy conventional explanations from theories like the Big Bang or stellar formation. Some examples include overweight planets, planets orbiting small red dwarf stars, but with sizes about 9 times that of Jupiter, challenging the theory that gas and dust in the protoplanetary disk are proportional to the star's mass. Quantum physics stars, stars exhibiting both particle and wave characteristics, akin to electrons in quantum physics. Phenomena like interference patterns, observed in the double-slit experiment, manifest in stars, contradicting classical physics. Ultra-high-energy spaceships, unidentified spacecraft with an energy level of 320 AF, defying explanation within current physics. These celestial anomalies surpass scientists' expectations, questioning our understanding of the universe's origin and evolution. It underscores the limits of prevailing theories and beckons exploration of alternative possibilities. Quantum mechanics serves as a crucial tool in comprehending the internal structures of stars and the formation and evolution of the cosmos. This field, which studies the behavior of subatomic particles, provides precise explanations for phenomena that classical mechanics cannot elucidate. Quantum mechanics significantly influences diverse scientific and technological domains, such as understanding the properties of solids and the principles behind semiconductors. Quantum mechanics plays a pivotal role in unraveling the mysteries of star formation, evolution, and cosmic phenomena. By predicting and comparing aspects like a star's mass, temperature, and reactions, quantum mechanics aids in explaining various cosmic phenomena, including nuclear fusion reactions powering stars, calculating the lifespan and evolution of stars, and studying events like supernova explosions and black holes. Moreover, in cosmology, quantum mechanics is indispensable for exploring the initial conditions of the universe, the distribution of matter, cosmic expansion, acceleration, and the fate of the cosmos. Thus, quantum mechanics proves its significance across a spectrum of physics, from the microscopic to the macroscopic, providing insights that contribute to our understanding of the universe.
In the cosmic tapestry, forces unseen. A dance of powers, vast and serene. A universe governed by secrets untold. In the grand theater of mysteries unfold. Expansion abrupt, a cosmic ballet. In the era of swift, celestial display. No center, no end, just infinite sway. A cosmic waltz in the vast astral array. The Hubble whispers its constant refrain. A cosmic heartbeat in an infinite terrain. A discrepancy noted, a scientific quest. To fathom the universe, we're put to the test. James Webb peers through the infrared gaze. Galaxies distant in the cosmic haze. A new measure, a celestial grace. A dance with the cosmos, an intricate embrace. Standard candles flicker, remnant rays glow. In the cosmic ballet, the Hubble's ebb and flow. 69, 73, the numbers unfold. In the vast cosmic story, their mysteries told. Scientific minds in dialogue engage. A cosmic riddle on the science stage. The universe expands, a lyrical theme. In the poetic dance of the cosmic dream. Today, let's delve into the forces governing the cosmos, the era of rapid cosmic expansion, and the enigmatic concepts of the universe's center and its limits. Don't forget to subscribe, like, and turn on notifications. Your support fuels the creation of these videos. Hello, there are 4 fundamental forces that dominate the universe: gravity, electromagnetism, the strong force, and the weak force. Each force has distinct characteristics. Gravity, it is the force acting between 2 objects with mass, and it is inversely proportional to the square of the distance between them. The hypothetical particle associated with gravity is called the graviton, although it has not been discovered yet. Gravity plays a crucial role on the largest scales in the universe. Electromagnetism, this force operates between 2 particles with electric charge, and it also follows an inverse square law with distance. Photons mediate the electromagnetic force. Electromagnetism determines the structure of atoms and molecules and governs various phenomena in our surroundings. Strong force, acting between quarks, the strong force becomes stronger as particles move farther apart. Gluons mediate the strong force, and it is responsible for the composition of protons and neutrons, enabling processes like nuclear fusion and fission. Weak force, this force acts between quarks and leptons and is effective only at short distances. W and Z bosons mediate the weak force, which is responsible for processes such as radioactive decay, and the generation of energy in the sun. These 4 forces have different strengths and ranges, allowing them to explain a wide array of phenomena observed in the universe. In the cosmos, the origin of the rotational motion observed among celestial bodies, galaxies, planets, and satellites can be attributed to the following. Orbital motion, revolution, celestial bodies move in elliptical orbits due to the gravitational attraction between them. The cause of orbital motion lies in the swirling and collisions of matter that existed in the early universe. During this phase, matter rotated to conserve angular momentum and, under the influence of gravity, coalesced, leading to the occurrence of orbital motion. Spin, rotation, this is the motion where a celestial body rotates around its own axis. Similar to orbital motion, the origin of spin can be traced back to the swirling and collisions of matter in the early universe. Matter rotated to conserve angular momentum, and through the influence of gravity, it coalesced, resulting in the initiation of spin. In essence, the source of rotational motion among celestial bodies in the universe can be attributed to the swirling and collisions of matter that existed in the early universe. The assumption that there were no swirling and collisions of matter in the early universe contradicts the laws of physics and is an unrealistic scenario. However, in a hypothetical situation where such conditions are assumed not to exist, the two objects could be attracted by gravity and have the potential to collide. The likelihood of collision depends on factors such as the masses of the two objects, the distance between them, initial velocities, and initial directions. For instance, if the two objects are sufficiently distant or moving in a direction that traces a circular orbit at a high velocity, they may not collide and continue to revolve. The swirling and collisions of matter in the early universe can be explained by the Big Bang theory. According to this theory, the universe originated from an extremely small and dense state with very high temperature, approximately 13.787 plus minus 0.020 billion years ago. Subsequently, it began to expand and cool continuously. After the Big Bang, the early universe was in a state where energy and matter were evenly distributed. However, as the universe expanded, slight density variations emerged. These variations, under the influence of gravity and other forces, triggered the swirling and collisions of matter. In this process, matter rotated to conserve angular momentum and, influenced by gravity, coalesced. The atoms and particles formed in this way eventually gave rise to the creation of stars and galaxies. Scientific theories describing the early history of the universe are based on the Big Bang theory, general relativity, particle physics, and other frameworks. These theories make predictions about the temperature, density, expansion rate, types and quantities of matter, cosmic background radiation, and more. Scientists can validate these predictions by comparing them with observational results, providing a comprehensive understanding of the early universe. After the Big Bang, the early universe existed in a state of extremely high temperature and density. At this point, it is believed that the universe was governed by a unified force encompassing the four fundamental forces: gravity, electromagnetism, strong force, and weak force. However, as the universe expanded and cooled, the four forces gradually separated. During this process, the universe underwent a period of rapid expansion known as the inflationary epoch. At the end of the inflationary epoch, the universe remained extremely hot. Energy and matter were evenly distributed, and there was the possibility of mutual transformation between energy and matter. During this time, the universe was dominated by radiation energy, with the density of radiation much higher than that of matter. At this stage, atoms did not yet exist, and fundamental particles such as quarks, gluons, electrons, positrons, and neutrinos were present. As the universe continued to expand and cool, quarks and gluons, under the influence of the strong force, formed the building blocks of protons and neutrons known as hadrons. The universe was then dominated by hadron energy, and the density of hadron energy was similar to that of radiation energy. During this period, matter and antimatter coexisted in equal amounts, undergoing collisions and transforming into energy. Further cooling of the universe led to the breaking of the symmetry between matter and antimatter. This was due to the different rates of creation and annihilation between the two. At this point, the universe was dominated by lepton energy, with the density of lepton energy higher than that of hadron energy. Electrons, positrons, neutrinos, and other leptons were present during this phase. Continued cooling resulted in the annihilation of electrons and positrons, converting into radiation energy. The universe was once again dominated by radiation energy, with the density of radiation energy higher than that of lepton energy. During this time, neutrinos, protons, neutrons, electrons, and other particles were present in the universe. Approximately 3.8 billion years later, the temperature had decreased enough for protons and electrons to combine, forming hydrogen atoms in a process known as recombination. At this point, the the universe was dominated by matter energy, with the density of matter energy higher than that of radiation energy. The universe contained hydrogen atoms, helium atoms, neutrinos, and other particles. Following recombination, the universe became transparent. The radiation energy first emitted during this period remains as the cosmic microwave background radiation observable today. At this time, the universe had slight density variations, leading to the swirling and collisions of matter under the influence of gravity and other forces. Matter coalesced, forming atoms and particles that eventually gave rise to stars and galaxies. This detailed explanation of the early history of the universe is based on the contributions of numerous scientists and researchers. The Big Bang theory was initially proposed by Belgian priest and physicist Georges Lemaitre in 1927. General relativity was completed by German physicist Albert Einstein in 1915. The Standard Model of particle physics was developed by numerous physicists from the late 20th century to the early 21st century. These theories play a crucial role in explaining the early history of the universe. Let me provide you with a detailed explanation of gravity, the force that governs the universe. Gravity is a force that acts between all objects with mass, proportional to the product of their masses and inversely proportional to the square of the distance between them. While the hypothetical particle associated with gravity is believed to be the graviton, it has not been discovered yet. Gravity plays a crucial role on the grandest scales in the universe. Throughout the evolutionary process of the universe, gravity has been instrumental in bringing widely dispersed matter together, forming stars and planets. This gravitational cohesion allowed other forces such as the strong and electromagnetic forces to manifest in the material world. The formation of structures like stars and galaxies is a consequence of the two essential conditions for the emergence of complex systems, the density of matter and the flow of energy. Gravity also exerts its influence on time and space. According to the theory of general relativity, gravity bends space and slows down time. In regions with strong gravity, time passes more slowly, and light is bent. These phenomena can be observed through gravitational lensing effects or the detection of gravitational waves. Moreover, gravity gives rise to intriguing phenomena such as black holes. Black holes are regions where gravity is so intense that even light cannot escape. The interior of a black hole remains unexplored, posing the challenge of the information paradox. Understanding black holes necessitates new physics, including theories such as string theory or loop quantum gravity. In summary, gravity shapes the universe by bringing matter together, enabling the formation of structures, influencing the fabric of space and time, and giving rise to mysterious phenomena like black holes. An in-depth understanding of gravity involves exploring cutting-edge theories and addressing unresolved questions in physics. Let me provide you with a detailed explanation of electromagnetism. Electromagnetism is the force that acts between two charged particles and is inversely proportional to the square of the distance between them. The mediator particle associated with electromagnetism is the photon. Electromagnetic force plays a crucial role in determining the structure of atoms and molecules and various phenomena in our surroundings. Electromagnetism unifies electric and magnetic forces into a single force. The electric force repels like charges and attracts opposite charges. The magnetic force acts between objects with magnetic polarity, repelling like poles and attracting opposite poles. Moving charges generate a magnetic field, and a magnetic field can induce the movement of charges. For example, a current flowing through a wire produces a magnetic field, and bringing a magnet close to the wire can induce current flow. This phenomenon is known as electromagnetic induction. Electromagnetism can also transmit energy in the form of electromagnetic waves. Electromagnetic waves are generated when electric and magnetic fields oscillate perpendicular to each other. Examples of electromagnetic waves include visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. In summary, electromagnetism is the force between charged particles, mediated by photons. It unifies electric and magnetic forces and is fundamental to understanding the structure of atoms, the behavior of magnets, electromagnetic induction, and the transmission of energy through various forms of electromagnetic waves. Let me provide you with detailed explanations for both the strong force and the weak force. Strong force. The strong force is a fundamental force that acts between quarks, the building blocks of protons and neutrons. It becomes stronger as the distance between quarks increases. The mediator particle for the strong force is the gluon. This force is crucial for the formation of protons and neutrons, which, in turn, allows for processes like nuclear fusion and fission. The theory that describes the strong force is quantum chromodynamics, QCD. QCD explains how quarks and gluons interact through the strong force. Quarks and gluons have a property called color, which comes in three types: red, blue, and green, as well as their respective anti-colors. The exchange of gluons between quarks involves changes in color, and quarks always exist in a color-neutral state known as color confinement. The strong force exhibits a unique characteristic known as non-abelian or non-decaying force, meaning it becomes stronger at longer distances. This leads to the phenomenon of asymptotic freedom, where quarks and gluons are freely moving at short distances but confined within particles at longer distances. Quark confinement is responsible for the formation of hadrons, such as protons and neutrons. Weak force. The weak force, also known as the weak nuclear force, acts between quarks, leptons, like electrons, and neutrinos. Unlike the strong force, the weak force weakens as the distance between particles increases. The mediator particles for the weak force are the W and Z bosons. The weak force is responsible for processes such as beta decay in nuclei. The theory that describes the weak force is part of the electroweak theory, which unifies the electromagnetic force and the weak force. This unification is a key component of the Standard Model of Particle Physics, which categorizes the fundamental particles and forces in the universe. Similar to the strong force, the weak force operates through the exchange of force-carrying particles. In the case of the weak force, W and Z bosons are exchanged, allowing for the transformation of quarks and leptons from one type to another. In summary, the strong force binds quarks together within particles like protons and neutrons, while the weak force is responsible for processes involving the transformation of quarks and leptons. Both forces play essential roles in understanding the behavior of particles at the subatomic level. Let me provide detailed explanations for both quantum chromodynamics, QCD, and quantum field theory, QFT. Quantum chromodynamics, QCD. Quantum chromodynamics, QCD, is the theory that describes the interaction of quarks and gluons through the strong force. Quarks and gluons possess a property known as color, analogous to the three primary colors, red, blue, and green. However, unlike ordinary color, quarks and gluons must exist in a color-neutral state. This means that a quark cannot exist individually but must always combine with other quarks to form color-neutral particles, such as protons or neutrons. The force carrier associated with the strong force in QCD is the gluon. Gluons mediate the strong force between quarks and other gluons, transferring color information and holding quarks together within hadrons. The strong force becomes stronger as quarks move apart, a phenomenon known as asymptotic freedom, which is a key feature of QCD. QCD is an integral part of the Standard Model of Particle Physics, providing a framework for understanding the behavior of quarks and gluons and their role in the formation of hadrons. Quantum field theory, QFT. Quantum field theory, QFT is a theoretical framework that combines quantum mechanics with special relativity to describe fields and particles in a relativistic quantum mechanical manner. In QFT, fields are defined at every point in spacetime, representing physical quantities such as the electromagnetic field or the quark field. Fields in QFT are quantized, meaning they are described by quantum operators, and particles are treated as excitations of these fields. For example, the quantized electromagnetic field gives rise to particles called photons. The theory allows for the creation, annihilation, and interaction of particles, providing a comprehensive description of the fundamental forces and particles in the universe. QFT includes various types of fields, such as scalar fields, spinor fields, and vector fields, each associated with specific types of particles. The fundamental principles of QFT involve the Lagrangian formalism, Feynman diagrams, and the concept of renormalization to handle divergent integrals arising in perturbative calculations. Both QCD and QFT are essential components of the Standard Model, which successfully describes 3 out of the 4 fundamental forces in the universe: strong, electromagnetic, and weak forces, leaving gravity to be described by general relativity. These theories have played a crucial role in advancing our understanding of the fundamental building blocks of matter and their interactions. The question of where the center of the universe was when the Big Bang occurred is based on a misconception. The Big Bang was not an explosion at a specific point in space, rather, it was the rapid expansion of the entire universe from an infinitely small and hot state. Therefore, the concept of a center of the Big Bang does not exist. The Big Bang happens simultaneously everywhere in the universe, and the universe continues to expand. The Big Bang theory explains the evolution of the universe from its inception to the present. However, questions about what existed before the birth of the universe and why the Big Bang occurred remain uncertain. Answering these questions requires new theories in physics. Similarly, the question of where the edge of the universe is also based on a misconception. The universe did not start from a single point but rapidly expanded from an infinitesimally small and hot state. Therefore, there is no center or edge of the universe as we commonly perceive it. The universe is expanding everywhere simultaneously, and the observable universe has a boundary, approximately 93 billion light-years away. However, this boundary is not the actual end of the universe, and it's challenging to determine whether the universe has a definitive end or if it continues to expand infinitely. In summary, the concepts of a center or an end of the universe as commonly perceived do not align with the current understanding of cosmology. New theories and advancements in physics are necessary to explore and answer these profound questions. There is a claim that the scientific community was stirred by the recent interpretation that the expansion of the universe observed by the James Webb Space Telescope may not be as fast as previously thought. The rate of the universe's expansion is quantified by the Hubble constant, which describes the relationship between the distance and velocity of objects in the universe. The farther the distance, the faster the velocity, according to this constant. Multiple methods exist for measuring the Hubble constant, such as using specific celestial objects with standard luminosities, standard candles, or utilizing the remnant radiation from the early moments of the Big Bang. However, these methods yield different values, creating a discrepancy. The use of standard candles suggests a Hubble constant of approximately 73 km per second/MPC, while methods involving the remnant radiation estimate around 67 km per second/MPC. This difference is statistically significant and has substantial implications for our understanding of the theory behind the expansion of the universe. In response to this issue, the James Webb Space Telescope proposed a new measurement method. Since it can observe the universe in the infrared spectrum, it can capture images of galaxies located even farther away. Through this approach, the Hubble constant was measured to be around 69 km per second/MPC. This value falls between the previous two methods, providing a statistically compatible result. These findings reduce the likelihood of errors in the methods used to estimate the universe's expansion rate. They also suggest the need for a re-evaluation of the theory regarding the expansion of the universe. The scientific community is currently discussing the accuracy and reliability of the James Webb Space Telescope's measurement methods and whether a new model for the expansion of the universe is necessary.
The dancing space of galaxies, the mystery of interstellar realms. Celestial bodies woven with starlight, the cosmic wonders. The dance of particles, the sound of waves. Untold stories embraced by the cosmic embrace. Beautiful stars, the voice of their light. A silent moment in the fabric of the universe that moves our hearts. The subtle resonance of galaxies, the fragrance of interstellar space. A mysterious moment in the cosmos, the eternal beauty. In today's session, we will delve into the enchanting moments of the universe, the particle and wave nature of starlight, and the celestial bodies in interstellar space. Remember to subscribe, like, and turn on notifications, as they greatly support our video production. Andromeda Galaxy, Milky Way, Large Magellanic Cloud, and Alpha Centauri Galaxy are just a few of the many famous galaxies in the universe. Let me introduce some of them. The Sombrero Galaxy is a peculiar-shaped galaxy in the Virgo constellation, with a dust lane cutting across its disk, placing it as an intermediate type between spiral and elliptical galaxies. The Small Magellanic Cloud is a satellite galaxy of the Milky Way, located between the constellations of Tucana and Table Mountain in the southern sky. It is an irregular galaxy, its shape disrupted due to interactions with our Milky Way. The Triangulum Galaxy is a small spiral galaxy close to the Andromeda Galaxy, making it the fourth closest galaxy to our own. It is influenced by the gravitational forces of both the Milky Way and the Andromeda Galaxy, and a future merger is anticipated. The S Sculptress Galaxy is a satellite galaxy of the Milky Way, situated approximately 200,000 light-years away. It is an elliptical galaxy, elongated by the gravitational influence of our Milky Way. NGC 1300 is a massive barred spiral galaxy about 6 times larger than the Milky Way, located in the Eridanus constellation. It features 2 spiral arms extending from both ends of its central bar, with a smaller spiral galaxy at the center. M87 is a massive elliptical galaxy located in the Virgo cluster, one of the brightest and largest galaxies. It harbors a supermassive black hole, and jets emanating from this black hole have been observed. NGC 253 is a barred spiral galaxy in the Sculptor constellation, approximately 11 million light-years away from the Milky Way. It is known for its explosive star formation, containing substantial amounts of dust and gas. M51, the Whirlpool Galaxy, is a spiral galaxy in the Canes Venatici constellation, positioned about 23 million light-years away. Its beautiful spiral arms were formed due to a collision with the smaller galaxy NGC 5195. M81 is a giant spiral galaxy in the Ursa Major constellation, located around 12 million light-years away from the Milky Way. It bears a resemblance to our Milky Way and possesses an active galactic nucleus. M82 is an irregular galaxy in the Ursa Major constellation, situated close to M81. It emits powerful stellar winds and jets due to its interaction with M81. These are introductions to some of the famous galaxies mentioned. I will introduce the theory that stars are both particles and waves. Stars are composed of electromagnetic waves, similar to light. Electromagnetic waves exhibit wave properties, demonstrated by various experiments. For instance, the double-slit experiment shows diffraction and interference patterns when light passes through slits, characteristics of waves. However, electromagnetic waves also exhibit particle-like properties, as demonstrated by the photoelectric effect. The photoelectric effect occurs when light strikes a metal surface, causing electrons to be ejected. This phenomenon cannot be explained if light is purely considered as a wave. If light is considered as particles, the interaction of light particles with electrons in the metal can explain the phenomenon. Electromagnetic waves thus possess a duality of being both particles and waves, a concept explored in the field of quantum mechanics, which studies phenomena in the microscopic world. Quantum mechanics has properties distinct from classical mechanics. For instance, observation affects physical phenomena. In this manner, the theory that stars are both particles and waves stems from the duality of electromagnetic waves. This theory forms the basis of quantum mechanics. While stars are composed of massive celestial matter, this matter is made up of electromagnetic waves. Electromagnetic waves exhibit the duality of behaving like both particles and waves, depending on the context. For instance, within a star's interior, nuclear fusion reactions release tremendous energy in the form of gamma rays, a type of electromagnetic wave with much shorter wavelengths than light. Gamma rays, acting like particles, collide or are absorbed, transferring energy. On the surface of a star, electromagnetic waves manifest as waves. When gamma rays interact with other particles, their wavelengths elongate, transforming into light. Light, as a wave, exhibits phenomena like interference and diffraction. The color of light varies based on the wave's speed and direction. Thus, stars are comprised of electromagnetic waves, and these waves exhibit duality by behaving as both particles and waves. The theory that stars are particles and waves is fundamental to understanding the diverse manifestations of electromagnetic waves within a star's interior and on its surface. While it is correct that the constituents of a star's structure emit both particle-like and wave-like characteristics, the idea that the entire star is simultaneously composed of particles and waves is a misconception. Considering stars as a whole in this way goes beyond the scope of quantum mechanics, which primarily describes phenomena in the tiny, microscopic world. Stars are colossal celestial bodies, and the laws of quantum mechanics do not apply to them on a macroscopic scale. The notion that an entire star moves collectively as particles and waves is also incorrect. Stars undergo various movements such as rotation, oscillation, pulsation, or explosion. These motions are determined by multiple factors both within and outside the star, and they are intricately linked to the star's structure and evolution. A star appears as a single entity to our eyes, and the idea that it is a combination of particles and waves until observed otherwise is inaccurate. Even in binary or multiple star systems, where stars form pairs, each star exists as an independent entity. While it is true that the constituents of a star's structure, including light and particles, exhibit the duality of being both particles and waves, it is essential to clarify that the entire star does not simultaneously exist as particles and waves until observed. I will introduce comets and meteor showers. Comets. Comets are small celestial bodies composed of ice, dust, and other volatile compounds, orbiting the Sun and the Solar System. As they approach the Sun, they undergo heating, causing the release of dust and gas, creating a distinctive tail. The tail of a comet extends in the opposite direction of the Sun and is categorized into plasma tails and dust tails. Comets are classified into short-period comets, which orbit the Sun periodically, and long-period comets, which make a single pass. One of the most well-known comets is Halley's Comet, which returns approximately every 76 years. Meteor showers. Meteors are cosmic particles and dust drifting in space, drawn toward Earth's atmosphere by gravity. Upon entering the Earth's atmosphere, meteors heat up due to friction with the air, producing a bright light. Most meteors are remnants of comets or asteroids, with meteoroids being generally small, ranging from fine sand-sized particles to larger rocky fragments. Meteors appear to radiate from a point known as the radiant, and meteor showers occur when the Earth passes through a trail of debris left behind by a comet or asteroid. Meteor showers are named after the constellation in which their radiant is located. For example, the Perseid meteor shower appears to radiate from the Perseus constellation. Both comets and meteor showers offer captivating celestial displays, showcasing the dynamic and interactive nature of celestial bodies within our solar system. I will introduce interstellar objects. The force that propels interstellar objects is gravity. Interstellar objects are celestial bodies originating from outside our solar system, having been influenced by the gravity of other star systems before entering our solar system. Once they enter the solar system, the gravity of the Sun affects these interstellar objects, altering their trajectories. Whether an interstellar object enters and exits the solar system is determined by its velocity and distance from the Sun. If an interstellar object had a higher velocity before entering the solar system compared to the rotational speed of the solar system, and if its distance from the Sun is greater than the size of the solar system, the interstellar object will pass through, following a hyperbolic trajectory. Examples of such interstellar objects include Oumuamua and the Borisov comet. On the other hand, if an interstellar object had a lower velocity before entering the solar system compared to the solar system's rotational speed, and if its distance from the Sun is closer than the size of the solar system, the interstellar object will stay within the solar system. Such interstellar objects follow elliptical trajectories. An example of this is the interstellar object known as 2020 SO. In summary, gravity is the force responsible for the motion of interstellar objects, and their entry into and exit from the solar system depends on their velocity and distance from the Sun. Oumuamua, discovered in 2017, is the first known interstellar object to pass through our solar system. Interstellar objects refer to celestial bodies from planetary systems outside our solar system. Oumuamua has an elongated shape, approximately 400 meters in length and 40 meters in width, resembling a cigar. Upon entering the solar system, Oumuamua exhibited rapid movement, reaching a speed of about 87 kilometers per second. The true nature of Oumuamua remains uncertain. Initially thought to be a comet, its lack of a visible tail led scientists to classify it as an asteroid. However, when it accelerated as it passed the Sun, scientists speculated that it might be a comet, with gas being released, a characteristic of comets. A research team from the United States suggested that Oumuamua could be a hydrogen iceberg, a substance not yet observed in space, formed in extremely cold regions known as giant molecular clouds. On the other hand, a research team from the Korea Astronomy and Space Science Institute contradicted this claim, arguing that Oumuamua could not be a hydrogen iceberg as such entities would either disappear before reaching the solar system or the formation process would be impossible. Thus, Oumuamua has sparked various debates and speculations. Scientists hope that studying Oumuamua may provide clues to unresolved mysteries in the universe, such as the origin of cosmic phenomena or the nature of dark matter. Penetrating the deep darkness of the galaxy, the light that emerges, the beautiful galaxies dancing in the infinite expanse of interstellar space. Stars, in their slow dance, sing the subtle coexistence of particles and waves, deeply moving our hearts. The celestial spectacle woven with starlight is filled with a poetic fragrance. The sound of particles and the resonance of waves give birth to the mysterious mysteries of the universe in the depths of space. Within this boundless cosmos, stars seem like keys opening tunnels through time. In the moment when particles and waves harmonize in song, we transcend the unknown boundaries of interstellar space, feeling the breath of the universe. Beautiful celestial bodies, with their special performance, enchant us, drawing us into profound contemplation of the mysteries of the universe. The enchanting moments of the universe feel like an embrace to our hearts. The radiant interstellar celebration, blending with the serenity of space-time, endures as an eternal beauty. All of this is connected to the secrets we whisper to the universe, and its beauty continues to unfold through the pupils of our eyes.